Hello and welcome back to Advent of Code 2018. Hello Bush 1G. We're on to day 12, so pretty much the halfway point. Okay. Let's see. Alright, day 12, Subterranean Sustainability. The year 518 is significantly more underground than your history books implied. Either that or you've arrived in a vast cavern network under the North Pole. After exploring a little, you discover a long tunnel that contains a row of small pots as far as you can see to your left and right. A few of them contain plants. Someone is trying to grow things in these geothermally heated caves. The pots are numbered with 0 in front of you. To the left, the pots are numbered -1, -2, -3. Okay, so it's just the number line. Your puzzle input contains a list of pots from 0 to the right and whether they do or do not currently contain a plant, the initial state. So hash is a plant. Starting from 0. This looks like some sort of game of life thing. Okay, fine. Okay. The puzzle input also contains some notes you find on a nearby table. Someone has been trying to figure out how these plants spread to nearby pots. Based on the notes, for each generation of plants, a given pot has or does not have a plant based on whether that pot and the pots either side of it, and the two pots either side of it, had a plant in the last generation. These are written as left, left, center, right, right, N, where L are pots to the left. Okay. Makes sense. So if a plant has empty spaces left, left, right, right, then it'll become empty. And if it doesn't satisfy any of these, or maybe it covers all possible states. Alright. So we just run it 20 times. Okay. Part 1 is easy, I think. For brevity, only the combinations which do produce a plant are listed. In this example, only the combinations which do produce it. Oh, because some remove a plant. Okay. What is the sum of the numbers of all pots which contain a plant? Okay. So, suppose we're going to use a hash set then. All right, let's begin. So, I want to read the initial state. So, so it'll be f dot read line I'm just thinking how best to do this. Okay, let's just do it like this. Let's say if it starts with initial line dot strip dot split, take the last token. That should be that whole thing. Okay. Otherwise, well, just do this. Let's say we'll split it by this symbol. Okay. All right, well, we want to keep this in a dictionary. So let's create one called transform, transition, whatever. So it'll be trans L equals let's just do R equals hash, true for hash, false for dot. Okay. I'm getting confused here. Okay, I think that's fine. Does that run? Let me get my coffee. Okay, so what do we do now? So we've got... I'm going to represent my plants like this. Let's say plants equals just a set. It's going to be a set of integers and contain plants. So we go for I enumerate initial if car equals hash plants dot add, just to be efficient. So I, right? So this contains all hang on. Let's have a think. Hello, DJ. Time for that marathon stream. Let's see. I've got probably only 2.5 hours. That would be enough to beat it if I were to use ChatGPT for every problem. Okay, so we've got a set of plants. Let's say let me have a look at these again. Every transition involves a plant, so let's say min x of any plant equals let's just say 0. Max x of any plant equals 0, and every time we add a plant, we update the min and the max. So for now, min will be 0. Max x equals max equals I. And min x equals I if it's the small one. Okay, so that will give us the min and the max plants. So now we have a set of plants, their locations, and the minimum one and the maximum one, which will help know where the full range is. So now we want to do the iteration steps. So for in range 20, because they want 20 steps. Do they include, so after 20 generations, so one generation means one spread? Zero is the first generation. Yeah, so they mean 20 executions after the initial one. Alright, fine. So we want alright, let's think then. If our min x if our min x happened to be like the right hand side of here, then we would have to do min x minus 1, minus 2, minus 3, minus 4. So min x minus 4 is the leftmost point we actually need to check. Because that guy could be affected by our min x. That guy who's not a plant could now become a plant. Oh, this one is important. But I just assume that by default. Otherwise you're going to get plants all over the place and infinite plants. Okay, so we need to check min x minus 4. So for x in range, so starting from min x minus 4 and ending on, and the same principle here. So if max x is the leftmost, it'll be max x plus 1, 2, 3, 4. So ending before max x plus 5. We now need to do simultaneous updates. So so I can't just change plants on the fly here, because that's going to affect what's in the number line for later iterations. So first I need to do a scan, see what each guy should become, and then simultaneously update them all. So I'm going to need to keep a track of adds and removes. All right. So x in range min x. Okay, so we're looking at x. Hang on, I've got this slightly wrong. This should be, sorry, these numbers are not quite right. That should be min x minus 2 and 3, because this only affects the middle one. So if, say, min x was yeah, if min x was a plant, or whatever, min x minus 2 would be the leftmost point which could be affected by it. Okay, yeah, that's right. Alright. So, for a given x, we need to construct a string. So it's going to be s equals hash if dx in plants, no, if, yeah, dx in plants, else dot, or dx in range, so it's going to be x minus 2 ranging to x plus 3. Okay. And we want to join that up. So that'll give us our 5-character string, which looks like one of these. It could be dot dot hash, whatever. It could be any of these. I don't know if this list actually covers every possibility. It's what, 2 to the power of 5, 30. Oh, it looks like it does. 32. Yeah, it does. Just in case it doesn't, though. Alright. So, if s in trans. Okay, so we look at the right-hand side of trans. So, if trans s is true, that means x needs to become a plant. So if trans s and x not in plants adds dot, that's an addition. Else if not trans, so this is saying it needs to be a not plant, and x in, but x is already in plants, then removes. Okay, so we do that, and then when we've done that, we've made a full sweep. All right, then we just go and change all this. So we say, for, let's say x in removes, plants dot remove x, for x in adds, plants dot add x. That's the more efficient way of doing it. But we also want to just min x equals the min of min x and x. We just want to update these. So if we find bigger or smaller x's than what we currently have, we need to update these. Alright. Just try running that. Okay. And then finally, we should end up with... we can try printing plants, just see what it looks like. So that's a list of indices. It should have some negative ones as well. Or not. Well, depends. I mean, it might not reach the negative. Alright, well... in what situation would we... so if we see a hash here, 2 hashes, on the right, then this should become a hash. The middle should become a hash. So we would expect 0 to become a hash on the next turn. It doesn't seem to reach the negatives though. I don't know. Maybe it's right. We try what did they want? They want the sum of all the pots. All right. Print sum of plots. 3725. I'm suspicious that there's no negatives because they included negatives, so you kind of would expect to delve into the negatives. Okay, it's correct, fine. Maybe we did delve into the negatives, but then we lost them again, because the plants can grow and die. Alright, you realize that 20 generations aren't enough. After all, these plants will need to last another 1,500 years to even reach your timeline, not to mention your future. After 50 billion generations, what is the sum of the... oh my god. What the heck? Alright, it's... we just have to find the pattern now. And OBS just disconnected. Wonderful. Just wait for it to reconnect. Did my internet actually cut out? Internet's working. Alright, well, I'll continue thinking while I'm, yeah, sorry, I disconnected briefly. Alright, so... we have to do what we did before, but 50 billion times. This is scary. So the sum of all... I don't immediately see what you're supposed to do here, because, what's the pattern? $50 billion. Can't do 50 billion steps. You can just try seeing how fast this actually goes. But it's not going to complete. So if... Alright, let's just see what happens. It's not even reaching 1 million. Yeah, because it's a lot of plants, isn't it? Oh, because we've got negatives. So negatives plus positives cancel out. So it's a question of finding the symmetry. But it's not going to be... I think I got disconnected briefly. I think that's what caused it. So over time, so these are all positives, but over time it will extend into the negatives as well. So the sum of the negatives with the positives will be 0. Well, I mean, if there's a plant at -5 and there's a plant at 5, then those sum to 0. So I'm guessing, even if we run this 50 billion times, you reach a stage where there's a lot of cancelling out. But it won't be perfect, so there's going to be some offcuts either side. So we've got to work out what's left after 50 billion. What? This is So I actually have to kind of really look at this input, because if it's just... Let's just try running it 100 times then. So let's have a look. There's no negatives. 6493. So 3725 was 20. 100 is 6493. Try 1000. 62293. 10,000. taking a long time. I guess because it's really growing. $620293. What the? These are interesting numbers, aren't they? Look. All the plants are centered around are all close to 10,000. I think I'm seeing the pattern. I don't know why that pattern exists. Well, what's really causing that pattern, but there is some sort of pattern. If I just guess the pattern and try it, so let's do this. Let's say print. So that's how many steps I'm doing, 10,000. So they seem to deviate around 10,000. So if I just change it to print, let's say, sorted x minus steps. So steps equals 10 equals 1,000. No. So x minus steps, sort it. I want to see what this looks like. I bet it looks like the same every time. Minus 88, minus 85, minus 82, minus 79. $62,293. How big is plants as well? $62. Interesting. So if I change to 1001, still 62. And it looks like we've just added okay, minus 88, minus 85, minus 82. And at the top end, it's 93, 96, 99. So if I try 2000. Minus 8, minus 85, minus 82. This is the stable. Fine. This, for some reason, it stabilizes here. Okay, let's assume that's the answer then. But we need to translate back to Okay, so we want run it 1,000 times. That will get us a list of plants. So we want to do sum of plants plus so we know that 2000 is 124293. That's the answer we're expecting. So I'm going to test this theory. So instead, I'm going to set steps to 2000, but I'm not going to run it at 2000 times. I'm going to run it 1000 times to get the stable state, which is like what this looks like. And then I'm going to extrapolate to see what 2000 should look like. So we should just use the same array as before, but we have to add steps for each item in the list. So it's going to be steps. Oops. It's going to be steps times length of plants. So we're expecting 124293. Not quite. Hang on. What's wrong with this theory? Print sum of plants plus an extra 2000 for each item in the plants. Is this array exactly the same? Let's test this then. So for in range 2000, let's do print list sorted x minus hang on, let me have a think this over. All right, go back to 1000. So 1000. Do that. Print list sorted x minus 1000. All right, try that. Take that out. Print sum of... Oh, I see the problem. Hang on. Okay. Let's say stable array equals this, because I was taking sum of plants. That's not right. We need sum of the stable array. So it's going to be list sorted x minus 1000. Okay, so here's the theory. We run this 1,000 times. We reach a stable state. And that's the stable array. And then for 2,000, to get 2,000, just print that. We want to do sum of stable array plus steps, which is 2,000, times length of stable array. Run that. Ah, that's it. That gets us 2,000. And we checked earlier because we ran it 2,000 times and we got 124293. But if I run it 1,000 times, just get the stable array and then use that to get 2,000. So it works. I don't know why it works. It seems... I think if you look into this, probably what's happening is you just get a stable state which is just translating forward by one space each time. And if you know it's doing that, then all you need to do is subtract the number of steps you've taken. So if I want to get 5 billion, we do 5, 1, 2, 3, 1, 2, 3, 1, 2, 3, 50 billion or more. Be that. Wow, that was a good problem. It's not, I mean, I still don't really know the mathematical reason why you would know that it eventually does that. I think you can't. I think it's just specially designed that it would do that. I think if these were different somehow, because there's nothing special about going to the right, is there? It could have been going to the left. If these were opposite way around, if every one of these was mirror image, then it would be translating to the left. And I'm pretty sure you could make it so that it would go do neither. It would just spread in both ways or do crazy things. I think he's specially designed it so that it'll follow a certain pattern, but if you look at this, it's not obvious that it'll do that. You have to just test it and see. Yeah, that was a really good problem. I was completely stumped at first, like I didn't think it was possible. Because I just assumed plants would just spread unpredictably. But if we look at our stable state, what's actually happening? Minus 88, minus 85, minus 82, minus 79. It's every 3. So the moment you get to one plant every 3 spaces, you are using that one. So the ones in the middle stay put. No. 1, 2, 3. No, this is not every 3. Hang on. So like this. So that stays put. That one. Ah. So if you're sitting here, and there's a plant to the left, and there's a plant 2 spaces ahead, then you will become a plant. Alright, so that one will become a plant. I'm guessing this one disappears. Let's see. So if you've got 2 spaces to the right, and to the left you have 2 spaces. This one, you disappear. Yeah. So you can see, yeah, it translates to the right, but it's not obvious immediately. You have to actually try and see. Nice. That's a really nice problem. Alright, on to 13. Let's have a look at the leaderboard for that. Well, it doesn't tell me much. I mean, some people, I'm sure that a lot of people just realized the trick. But did people find it hard? 12. Harder than 11, yeah. It looks like 14. It looks like 14 stumped a lot of people. No, sorry. The other way around. It looks like 14 is easy. It looks like 13 stumped people. Oh dear. Okay, fine. I think it takes longer because you can't just write a program, press run, and get an answer. It's a two-step process at minimum. You have to run, see something, adjust, and run. That's probably why. So the people at the top end of the chain had to actually adjust their code after what they saw. Because he could have equally made it so that it was translating to the left instead. Or doing something else altogether, like spacing out, I don't know, 2 spaces instead of every 3 spaces. Okay. Oops, 13. Minecart madness. Oof. Oof. Don't like the look of this. Oh god. Okay. Donkey Kong time. Yeah, pretty much. It looks like we're working out where these minecarts crash. I just don't like this, well, we'll see what we're actually dealing with here. Minecart madness. A crop of this size requires significant logistics to transport produce, soil, fertilizer, and so on. The elves are very busy pushing things around in carts on some kind of rudimentary system of tracks they've come up with. Seeing as how cart and track systems don't appear in recorded history for another 1,000 years, the elves seem to be making this up as they go along. They haven't even figured out how to avoid collisions yet. You map out the tracks and see where you can help. Tracks consist of straight paths and curves and intersections. Okay. Curves connect exactly 2 perpendicular pieces of the track. At an intersection, a cart is capable of turning left, turning right, or continuing straight. Oh, so mine carts can even choose where to go. Several carts are also on the tracks. Carts always face either up, down, left, or right. Let's have a look at our initial map then. Oh my god. Okay. I'm guessing the mine carts are always on a straight piece. They're not standing on a curve or an intersection, because that would make things confusing. I mean, it seems that way. Ah, yeah. Okay, it's always a straight path underneath the cart. Okay. Each time a cart has the option to turn, it turns left the first time, straight the second time, right the third time. Okay. So each cart keeps track of which turn it's going to take next. Carts all move at the same speed. They take turns moving a single step at a time. They do this based on their current location. Carts on the top row move first, from left to right. And then carts on the second row move. And carts on the third row. Okay. And that matters because you could have collisions where well, it's the difference between a cart crashing into another one's stable stationary position or that first cart getting out of the way so that the new cart can move in. So timing matters. All right. First, the top cart moves. Then the bottom cart moves, okay. The first cart moves down, and the second cart moves up, right into the first cart, colliding with it. After following their respective paths for a while, the carts eventually crash. To help prevent crashes, you'd like to know the location of the first crash. Might not be as complicated as it seems. It's just really horrible looking graph. Okay. Yeah, it might not be too bad actually. We just... Copy that. Alright then, let me try and do something at least. That is the graph. So we can just store all this in a... Okay, let's have a look. There's something I need to do. I might need to take a longer BRB, maybe 5 minutes. Should I do that now, or let me at least read the input. That's always nice to get done. I don't know who's on the loudspeaker outside. Loudspeaker, I mean megaphone. Let's do this. On grid equals for line in f.readlines, we want to do grid dot append, let's say list of line dot strip. So that's going to make it so that make it a list, because we actually want to change some of these. For example, the where the minecarts are standing, I want to replace those characters with the actual straight lines, because that's going to throw us off. But I mean, wait, no, we can do that. We can do that in one line here. We can say let me think. No, because we need to keep track of... No, okay. Just do what I was doing the first time. And we need to record the positions of the minecarts. Right, so we need to extract the minecarts from this map. So I had to think about it. I don't think part 1 is actually that hard. We just need to handle all the different cases of what they run into. So we have the first thing we need to do is just extract all the minecarts from the strings. So we need to say for row in for y in for y row in enumerate grid for x in range length of grid 0. So I'm guessing all. We want to keep the white space at the end. That's one important thing. Actually, no, it doesn't matter. It doesn't matter about the white space at the end. But we can do... Oh, yeah, why am I doing this, though? Do it in row. Whoops. Row. Length of row. Because the white space doesn't matter, because the minecarts can never enter this white space anyway, so we don't need to store it. It is kind of weird that the grid is not a square. It's kind of... But it doesn't matter. Okay, if row x in, so we've got this, that means it's a minecart. Okay, so so for each minecart, there's actually several things we need to keep track of. We need to keep track of its position, its direction, and whether it's going to turn left, forward, or right at the next junction. So we're going to have to keep a dictionary. Minecarts equals this. Or just a list. So position, well, okay, minecarts dot append. All right, so the position will be x, y. The direction will be row x. That would just be the symbol. Okay, a lot of noise going on outside. In fact, we could do... No, let's use a mathematical directions. Let's say translate these to so left translates to -1, 0. Right translates to 1, 0. Space these out properly. V translates to 0, 1. And whatever that thing's called, I keep forgetting. Circumflex translates to... No. What was it? Caret. Translates to 0, -1. So we want to get directions for that symbol. So that gets the vector instead of the symbol. Then we can actually use it for calculations. Unexpected argument. Pronounced like the veggie. Carrot. Okay. Why doesn't it like this? Oh, because this should be a tuple. And we also want to keep track of whether we're going to turn left, forward, or right. So they said we start left, so let's just give it the parameter left. Circumflex is usually the caret when it's above a letter. Oh yeah. So that's everything we need to know about a minecart. So we've extracted that. Now we can fix the grid by putting in a line instead. Right, so if row X is one of the horizontal ones, then replace grid Y, X with or is it hyphen? Yeah. And otherwise it's vertical line. Okay. Print minecarts. Okay. We need a couple of other things. So we need to know how to turn left. If you've got a direction, which is, say, this, and you're being told to turn left, we need to know where you end up. So let's make a left map, which maps, okay, starting for each of these. So if you are that, then you end up oh yeah, I can use the symbols to help me. So if you're going left, you should end up down. So you should end up with that. If you are going right, you should end up going up. If you are going down, you should end up going right. And if you are going up, you should end up going left. And then right will just be the same, but we can say V maps to K for K V in left to items. So it swaps them around. Okay, so now we know how to all right, and the other thing is we need to know if my so we have this notion of a cycle. If I'm going to take a left at the next turn, then after I've done that, we need to change left to forward or whatever. Hang on, what's the pattern? Left, straight, right. Left, straight, right. Left, straight, right. Okay. So we want to do it like this. We want to say if you're a left, then next time you'll change to a straight. If you're a straight, then next time you'll go right. And if you are right, you will go left. So that saves us a lot of if conditions later on. We can just pull up the replacements from these maps. All right. So now what? We want to do a while true loop. So this goes on forever until we crash. So I think the first thing we should do is sort the minecarts by row and then by column, because they want us to process them in that order. And that the order will change, so at the start of each iteration of the while loop, we need to do minecarts.sort key equals lambda. We've got a tuple, so we would take... So what did they... How did they want it? We want top row, so we want the minimum y value and then the minimum x value. So it's going to be t0, 1, t0, 0 for the x value. That's the key to sort on. Alright. So we sort. Okay. And now I minecart in enumerate Minecraft. Why is Minecraft a word in Python? Why did autocomplete think I was gonna write Minecraft? Why is that programmed into the IDE? Oh, because I actually wrote Minecraft here. Oh my god, so stupid. Okay, the IDE was behaving correctly. I was wondering why is it suddenly said Minecraft? Where did that come from? It's like they put Minecraft into its spelling, well, into its vocabulary. All right. For I minecart in enumerate minecarts. Apparently you really want to play some Minecraft. I do, actually. I need to get back into Minecraft. I've never actually beaten the game, and I kind of want to. Actually, I've never beaten the game solo. I've beaten the game co-op once. But I'll have to play hardcore, because that's the way it should be played. Okay, so for each minecart, we need to process it by one step. So let's unpack its stuff. So position, direction, turn, let's just call it turn, equals minecart. So that will unpack the three things. The easy one is new position. New position equals pos 0 plus direction 0, pos 1 plus direction 1. Alright, that's new pos done with. At this point, we need to... How many minecarts do we have? Not many, so it doesn't matter if we do a for loop here. We want to say if there is another minecart in the list with this position, then this is where we crash. Instead of making this Okay, let's make this a method. Define get crash. All right. If any for T in minecart. So if any minecart has its position equal to our new position, that means we have a crash. So we immediately say, what did they want? The location. All right. Return new pause. That's where the crash is. Okay. Okay. So now we need to check what type of we need to check what space we're moving on to. So the only things we care about are the corner pieces, these ones, and the intersections. If we walk onto a horizontal line or a vertical line, we don't need to do anything because it's safe. It's still going the same direction. Nothing's changing. All right. So we don't need to change direction and turn in those cases. So if grid of, okay, let's unpack this. X, Y equals new pause. If grid Y X is, let's do each of these one by one. So /. Okay, so that would happen if either we've come from the so if we came from the left, that would force us to turn left. If we came from above, we would turn right. If we came from below, we would turn right. If we came from the right, we would turn left. Okay, so we have to say if direction in, so there's two possibilities that will cause us to turn left. Either we are going to the right, or we're going to the left. We want to say new direction equals left of the current direction. So we want to turn left. Otherwise, new direction equals right. Okay. New direction equals the old direction. So doesn't change if we don't do anything. So here we're overriding that. We say if it's that, we change left or right. Okay. Similarly, if it's a /, now if we come from the left or the right, we're turning right. Otherwise, we turn left. So that's that. Otherwise, and the most important one is if it's a plus, that's an intersection. All right. If so, we need to check our turn. If turn is left, then new direction equals left. We turn left and turn. Okay, we're gonna have to have a new turn. All right, this is not actually that complicated. I'm getting a rhythm here now. So, new turn equals cycle of the old turn, and the cycle handles that. All right. Elif turn is straight. We don't need to do anything if we're... Okay, so let's take this new turn outside of these ifs. Okay, so if we're going straight, we don't need to do anything. If we're going right, new direction equals the right direction. Okay, and either way, no matter what our turn was, we cycle the turn to the next one. Okay. Ah, we have to escape the backslash. There we go. And now it should be minecart's I is replaced with new pause, new direction, new turn. Minecrafts. Why do I keep typing Minecrafts? So at this point we should just print get crash. See what happens. All right, we've got a program crash, not the kind of crash we're looking for. If grid yx, huh? Apparently we've gone off the end of the map, but we shouldn't because these tracks should always keep us on the tracks. So the space we head into should always be a track. So somewhere we made a wrong turn and we're actually going off into the white space. I'm just going through the logic again. So grid yx, xy. Mm-hmm. Okay. Have I got these turns correct? So for some reason the new pause, we've gone to the right or something. No, not to the right. We've probably gone up into a white space. So we were standing on, I think the most likely place was we were standing on a corner, and for some reason, so if we are approaching from the left or the right, we turn left. Yeah. Wait, am I getting the right symbols as well? Is it V or is it capital V? It should be small v. Yeah, it is small v. Okay. Yeah, I'm guessing... Alright, so if we go on the backslash, then if we come from the left, we turn right. And if we come from the right, we turn right. Bottom up, we turn left. That's correct. Looks right. And if it's a plus... If it's straight, then we don't change direction. Ugh. I guess we're gonna have to print stuff. Okay, print. New pause. Grid. Wait, so just pause, new pause. Okay, just do that. And I don't know, direction. Alright, so the last thing we printed was this. Okay. So we're going up. Our position was 1211, and we went to 1210. 1, 2, 1, 1 would be on this row, and it would be here. It would appear that we've so it seems we came from below, from that junction. We went here, and then we went up instead of right. Or alternatively, we came from the right and we turned right. Either way, we end... 1, 2, 1, 0. So the new pause is 1, 2, 1, 0. But that should be fine. There's a 1, 2, 1, 0 is this row here. That character there. Why is that out of range? Maybe I need to... What have I messed up this grid? I've done line.strip, but that only strips the... white space from the end, doesn't it? Oh, it strips from the beginning! I've fallen into this trap before. Leading and trailing. Take off the strip. We don't need strip. Or just, you can specify strip new line characters. That's the only thing I want to strip. Alright. There we go. 63103. Uh, 63103. Correct? Alright, that took a while to unpack. Alright. There isn't much you can do to prevent crashes in this ridiculous system. However, by predicting the crashes, the elves know where to be in advance and instantly remove the 2 crashing carts the moment any crash occurs. They can proceed like this for a while, but eventually they're going to run out of carts. It could be useful to figure out where the last cart that hasn't crashed will end up. That doesn't sound hard. It could take a long time if there's 3 left, it might take a long time for there to be a crash, because they're running around this map. So... But I don't see any trick to speeding it up. So I think we just want to run it. Interesting. Could try... Someone needs to make that track in Factorio or something. Yeah, so when these competitions come out, a lot of people actually do that. They open up Minecraft or Factorio or things, and they remake the problem. Like, there was a falling sand problem, where you have sand falling, and it spreads out, just like it does in Minecraft. So someone rebuilt the same input in Minecraft to watch this, because the sand, when it drops on other sand, it falls to the left or the right. And people have used Factorio for like train-like things, and what else? there was one involving cranes picking up boxes and putting them in other places. There was actually a game which had a crane mechanic which was able to replicate that scenario as well. Well, there were some other good ones. I'm trying to remember what they were. Factorio comes up a few times. Factorio and Minecraft are the most common because Minecraft is blocks, so a lot of cube structures. You can do stuff with them. Okay, so for this, I guess we just run it as we've done. I don't see any clever shortcuts here because we kind of have to simulate every step. Like, okay, if you see that you're on a long stretch, then you kind of know where you'll end up in 10 spaces or so, but you can't really skip ahead because you've got other minecarts to deal with. Alright, so we'll just run it, see what happens. I think the biggest problem, the thing which is eating the most time for me is this line here. That's inefficient. I should be using a hash map for it. So if it takes too long to run, I'm going to have to replace that line here. But for now, let's say if there's any minecart that we've moved into, then what's the correct way to do this? I don't want to delete the minecart immediately. That's gonna mess up this order. That's why I should be using hash maps for minecarts. But maybe I should switch to doing that. Alright, if we stick with this, then we want to say, there could be 2 simultaneous crashes as well, or more than 2. So we have to make a 2 delete. Equals an empty list. If any we'll make it a set, I don't know. Okay, first, if our starting position is in 2 delete, that means someone crashed into us earlier before we had our turn, and we don't get to take our turn. So, continue. If any other minecart is in our new position, also we don't want to return here, then to delete dot add new our position to wait no. Oh, okay, I see. We don't have an ID number for the minecarts. Okay, fine. Just add the new position. So the position of the crash is key here. We're not saying, let's call it crash sites. What happens if 3 minecarts all arrive at a crash site? Ah. Now let me think this through, because if 3 minecarts are all heading for the same space on the same turn, the first 2 will crash, but then they are instantly evaporated, and then the third can actually pass. I think that's the correct rule. So okay, we need a couple more data structures here. Right. So I need one more thing here. So after we've created the minecarts, okay, we want one more data structure, which is going to say minecarts shouldn't be a list, it should be a dictionary. And it's a dictionary that maps position to the minecart's properties, which are just direction and cycle. Yeah. That allows us to efficiently look up minecarts by their position. Alright, so we want minecarts. Alright, so this will become minecarts XY equals, and then it will just be direction and cycle. Okay, that's that. And now we need to rearrange this, so we want 4 Okay, don't do that. Don't do that. For I in sorted minecarts.keys, sort the positions using this again. but not quite like that. So mapping, so a key will take the y value followed by the x value. Right, so we look over the keys in a dictionary without rearranging the dictionary. Okay, so we got position, minecart equals okay, so let's say for pos in sorted minecarts keys. Okay, so then we got direction turn equals minecarts at that that extracts the minecart at that position. So we're ranging over the different positions, and for each one we pull out the direction of turn of the minecart at that position. You're not allowed to have two minecarts in the same position. Okay. Now, I get rid of this. And now all the rest of the logic kind of stays the same. All right, here. So this is simpler. This, we just say if new pos in minecarts. That's a fast lookup rather than a linear time lookup. That means there's a crash. Okay, then what do we do? Now we can delete safely because we're not ranging over a list where things matter in order or whatever. If new pos in minecarts, okay, so that minecart we've crashed into now gets deleted. It never gets its turn. So we do delete minecarts new pos. Delete minecarts pos. We destroy the current minecart, and we can do that because we're not holding a reference to it. Maybe we can just want to see what happens here. So print new pos. But we keep going. And here, all this logic is the same. Take that out. New direction. All right, and here we say... So if we got this far, that means there was no crash. So minecarts new pos equals new direction, new turn. And then we have to make sure we delete the old pos. So here we want to continue to the next minecart. Ooh. No, we are holding a reference to the keys. So this will crash. Because... okay, fine. If pos not in minecarts. So if it got deleted before we could deal with it, skip this one. Okay. Now what? So that's just going to keep going. Is that safe? Yeah, because we're just this is not holding a reference to minecart to the table. It's just pulling out the keys as a new instance. So if we've deleted a minecart but it's still in this list, then it won't be in minecarts anymore, so we can just skip it. Otherwise, if we have a crash, we delete 2 things only. Print the position of the crash. 63,103. That was the answer, wasn't it, to the first part? Yeah, so it's still working correctly. And then we just carry on. So at what point do we want to stop? We want to stop when after this is all done. Here, if length of minecarts is 1, print minecarts.keys. That's just, they want to know the location of the final cart, so that's when we stop. Right, I have a... Okay, and return. Let's see. 16,134 is the last one. That was surprisingly quick. I thought that in the final, when there's only like 3 left, it might take absolutely ages for them to crash. Because, I mean, they could be going anywhere in this map. It's pretty indeterminate, so you're waiting for 2 minecarts in this map to crash. And they're following their weird rules, so I don't know. But it says they crashed, so I feel like that's probably the correct answer. Nice. Okay. That's a problem with easy logic once you get a handle on that crazy mind track. And like the horizontal and the vertical bars don't matter. I never even had to look at them. They could have been empty spaces. All that matters is the corners and the junctions, because those are the points at which you change direction. So, I mean, those lines could have been empty spaces, and it would still work. You just keep going until you hit a corner, or yeah, you just it's not. There's no clever algorithm here. You just have to do things in the correct order. I'm guessing if I had used an ugly list to keep track of the minecarts like I was doing originally, it might have taken too long to actually do that. Replacing with a dictionary lets me quickly look up, given any position in the map, I can quickly say whether or not there's a minecart there. That's the important thing. Before, every time I was doing that, I had to look through all the minecarts, check what positions there are, and see if one of them had the position I'm looking for. Now I had a proper dictionary key for each location, so I think that's the correct way to do it. But yeah, now I think that's a nice problem. It's not actually overly complicated. Even parsing the input is not that bad. There's just 3 symbols you got to look for, really, plus / and backslash. And there is actually quite a nice symmetry with all these turns and stuff, so it's not... You don't actually have to write too many cases. You would have to write more cases if I didn't use those dictionaries that I was using. And that's how I used to write code, not even that long ago, so... Keeping dictionaries at the top of your map saying, this is what happens if you turn left, it takes this vector to this vector, this vector to this vector. I didn't used to do that. And that means every time I had to turn left, I would have to write a bunch of if conditions saying if you're currently going up, you go left. If you're currently going left, you go down. And then later on, if you would have to turn again, I would have to do that all again. So a left dictionary and a right dictionary really simplifies things. Basically, what I'm getting at here is dictionaries. That's the key to success in most of these problems. Use dictionaries. Don't use lists. Use dictionaries. That is, I mean, on the job, that is actually a pretty good lesson. Just keep using dictionaries. Everything is dictionaries. Everything is key value mappings. Databases are just key value mappings. And I mean, when you do interview problems, they love asking questions about dictionaries, or asking questions where they don't mention dictionaries and they hope you use dictionaries, which is also important. I'm pretty sure when I interviewed at Google like a decade ago, I had 5 interviews. I'm pretty sure 4 out of the 5 interviews were about dictionaries. When I say dictionaries, I mean hash maps, but in Python they're called dictionaries. But the language agnostic term is hash map. Because if you can do a hash map, you can do anything. That's not true. I had to use a linked list a few problems ago. Which was a problem which was not solvable with a dictionary, actually. Alright, I've got to finish there. Because I've got to get to the gym, as always. Tomorrow I'm not going to the gym, though, so I might have more time to code. So that was 13. People found it harder. It's not surprising. I think people would be scared of that big, horrible track. But you can see that okay, 800 is relatively high. That means a lot of people solved part 1 but couldn't solve part 2. Understandable, I think. Dealing with crashes is one level of complication higher. Dealing with crashes correctly and efficiently makes this problem complex. So next time, it looks like 14 is an easy one, going by these stats. I could take a sneak peek. Wait, how do I... It looks like we've got... What are these? Beer mugs? Sneak peek. Digits of sums. It looks like we've got number theory here. Some sort of number pattern. Recipes, scores. It looks like some sort of iterative number process. Okay. So that was 2 problems today. All right, I mean, that's 2 problems a day. I'll get there by the end of the month, hopefully. All right. Thanks, DAJ, and I should be able to do another one tomorrow. All right. Thanks for watching. See you next time.